Hey math fans! Welcome to Math Olympiad Academy, your trusted space for advanced problem solving and logical reasoning. We sincerely thank our subscribers and all viewers for your continued support. In Lesson 32, we explain step-by-step how to determine the domain and the derivative of a function faster and cleaner. Moreover, we summarize a short recall about the problem, solving method, and at the end of the video, we attach a homework problem to practice. So, stick with us to discover this step-by-step method. The objective of this lesson is for students to, first, find the domain of a function that includes radical, exponential, and trigonometric terms. Second, compute the derivative at special points, like where the function is zero or has undefined parts, using the definition of the derivative. And third, determine the general derivative expression using logarithmic differentiation. In this problem, let f of x equal x times the square root of the quantity 2x plus 1, all divided by e to the power x times cosine cubed of x. First, find the domain of f, denoted domain of f. Second, find the derivative of f at x equals 0, denoted f prime at x equals 0, and then find the right-hand derivative of f at the point -1/2. Third, find the expression of the derivative of f, denoted f prime of x, for all x in the domain of f, excluding x equals 0 and x equals -1/2. Now, let us begin the solution. First, rewrite the given function. F of x equals x times the square root of the quantity 2x plus 1, all divided by e to the x times cosine cubed of x. To find the domain of this function, in the numerator, x is defined for all real numbers, but the square root of 2x plus 1 requires that 2x plus 1 be greater than or equal to 0. This means x must be greater than or equal to -1/2. In the denominator, e to the x is never 0 for any real number. However, cosine of x must not be 0 because it appears in the denominator. Let us recall that the domain of the function f is the set of all real numbers such that 2x plus 1 is greater than or equal to 0 and cosine of x is not 0. This gives x greater than or equal to -1/2 and x not equal to pi over 2 plus k times pi, where k is any integer. Therefore, the domain of f is the interval from -1/2 to positive infinity, including -1/2, but excluding all points of the form pi over 2 plus k pi, where k is an integer. Now question 2, the derivative of f at special points. First, consider x equals 0. We use the definition of the derivative. The first derivative of f at 0 equals the limit as x tends to 0 of the quantity f of x minus f of 0 all divided by x minus 0. Since f of 0 equals 0, this simplifies to f prime of 0 equals the limit as x tends to 0 of f of x divided by x. Substituting the expression for f of x, we get the limit as x tends to 0 of x times the square root of the quantity 2x plus 1, all divided by e to the x times cosine cubed of x all over x. This is the same as the limit as x tends to 0 of x times the square root of the quantity 2x plus 1, all divided by x times e to the x times cosine cubed of x. Now cancel the factor x in the numerator and the denominator. This gives the limit as x tends to 0 of the square root of the quantity 2x plus 1, all divided by e to the x times cosine cubed of x. Now substitute x equals 0. The square root of 2 times 0 plus 1 is the square root of 1, which is 1. E to the 0 is 1. Cosine of 0 is 1, so cosine cubed of 0 is 1. Thus, the limit equals 1 divided by 1 times 1, which is 1. Hence, the first derivative of f at 0 equals 1. This result confirms that f is differentiable at x equals 0. Likewise, the first derivative of f at -1/2 on the right equals the limit as x tends to -1/2 from the right of the quantity f of x minus f of -1/2, all divided by x plus 1/2. Since f of -1/2 equals 0, this is equivalent to f prime of -1/2 on the right equals the limit as x tends to -1/2 from the right of x times the square root of the quantity 2x plus 1, all divided by e to the x times cosine cubed of x, minus 0, all over the quantity x plus 1/2. This yields the limit as x tends to -1/2 from the right of x times the square root of the quantity 2x plus 1, all divided by the quantity x plus 1/2 times e to the x times cosine cubed of x. Now multiply both the numerator and the denominator by 2. Then, rewrite 2x plus 1 in the denominator as the square root of 2x plus 1 times the square root of 2x plus 1. Now, simplify by canceling one factor of the square root of 2x plus 1 from the numerator and the denominator. After this simplification, we obtain f prime of -1/2 on the right equals the limit as x tends to -1/2 from the right of 2x divided by the quantity square root of 2x plus 1 times e to the x times cosine cubed of x. As x tends to -1/2 from the right, the numerator 2x approaches 2 times -1/2, which is -1, while the denominator, square root of 2x plus 1 times e to the x times cosine cubed of x, approaches 0 from the positive side, because the square root of 2x plus 1 approaches 0 through positive values, e to the x approaches a positive constant, and cosine cubed of x also approaches a positive constant. Therefore, the entire expression tends to -infinity. So, the right-hand derivative of f at -1/2 equals -infinity. This shows clearly that f is not differentiable at the point -1/2. Before solving the third question about the derivative of f, denoted f prime or d of f with respect to x, let us recall in concise points. The derivative of f can be expressed in Leibniz notation as d of f with respect to x. In many cases, we also use Lagrange notation, denoted f prime of x. To find the derivative faster and avoid tedious calculations, we adopt a problem-solving method based on logarithmic differentiation, summarized below. To differentiate y equals f of x, first, apply logarithmic differentiation. Take the natural logarithm of the absolute value of both sides of the equation. This gives natural logarithm of absolute value of y equals natural logarithm of absolute value of f of x. Second, apply the properties of logarithms to expand the right-hand side as much as possible, turning products into sums, quotients into differences, and powers into coefficients. Third, differentiate both sides of the equation with respect to x. Fourth, multiply both sides of the resulting equation by y. Fifth, replace y by f of x to obtain the final expression for the derivative. Note that applying logarithmic differentiation is often faster and cleaner than using the quotient rule, which states that the derivative of f over g equals f prime times g minus f times g prime, all divided by g squared. Now, let us return to our question number 3 and apply logarithmic differentiation. Namely, the function f of x equals x times the square root of the quantity 2x plus 1, all divided by e to the power x times cosine cubed of x. We begin by taking the natural logarithm of the absolute value of both sides. This gives natural logarithm of absolute value of f of x equals natural logarithm of absolute value of the quantity x times the square root of 2x plus 1, all divided by e to the power x times cosine cubed of x. Now, apply the properties of logarithms to expand the right-hand side as much as possible. This yields natural logarithm of absolute value of f of x equals natural logarithm of absolute value of x plus 1/2 times natural logarithm of the quantity 2x plus 1 minus x minus 3 times natural logarithm of absolute value of cosine of x. Next, differentiate both sides with respect to x. The left-hand side becomes f prime of x divided by f of x. The right-hand side becomes 1 over x plus 1 over the quantity 2x plus 1 minus 1 minus 3 times sine of x divided by cosine of x. Since sine of x over cosine of x is tangent of x, we can write this as 1 over x plus 1 over 2x plus 1 minus 3 times tangent of x. Now, multiply both sides of the equation by f of x. This gives f prime of x equals f of x times the quantity 1 over x plus 1 over 2x plus 1 minus 3 times tangent of x. Finally, replace f of x by its original expression. This yields f prime of x equals x times the square root of the quantity 2x plus 1, all divided by e to the power x times cosine cubed of x, multiplied by the quantity 1 over x plus 1 over 2x plus 1 minus 3 times tangent of x. This expression is valid for all real numbers x belonging to the domain of f, except at x equals 0 and x equals negative 1/2, the special points we already examined earlier. Note: although this expression can be combined into a single rational function, we retain the expanded form to clearly show how each factor in the original function influences the derivative. Now, for practice, it's time for homework. Apply what we explained in Lesson 32 to find the domain and the derivative of the functions f of x and k of x given below. If you'd like, share your answers in the comments. We'd be thrilled to see your work. I hope you enjoyed this step-by-step solution. Keep practicing, share this lesson with your friends, and don't forget to subscribe to Math Olympiad Academy for more exciting math challenges. See you in the next lesson!